So today we will be discussing about big data, the meaning of big data and what it means. And to give us more industrial insight, we have an industry expert, John Hawkins. I hope I pronounced your name correctly, John, from
Yeah.
gettingdatascience.com. So this amazing website, I recommend you visiting that. And John will be telling us more about big data. So since this is the last week, of course, I would like to request you all to complete the course feedback form. We really appreciate your feedback and we incorporate your feedback to improve this course. Without any further delay, I would like to hand over the screen to John for his interesting presentation. John, the screen is yours.
Wonderful. Thank you, Bikesh. So I'll give you just a rough outline of what we're going to try to achieve in this talk. And keeping in mind that I've built this on from my understanding that Bikesh has given me of the kind of things that you've already discussed so far in this course. And it's largely about anchoring the idea of big data to the kinds of traditional analytics you've covered in more detail. So two primary goals in this talk is to talk about what is big data, why we might want to use it, and then how do we then incorporate big data approaches in a way that can complement traditional analytics that we'll do in industry. So what is big data? There's three things that I think are pretty important to keep in mind when thinking about this. The first is that the transition to big data analytics is in a large part about a larger scale shift that's been happening for quite a while. So if you think about back to, sort of 30 odd years ago when a lot of traditional business analytics was developed, a lot of organizations that had large database systems, they were typically sort of monolithic structures where key operational data was kept in a database that could be queried and for doing reporting. But many of the standard operations of a business were analog and not digital at all. But as we've moved to make more and more business operations happen online, where both the acquisition of customers, interaction with customers, the products they purchase, our interaction with suppliers, our interaction with sort of maintenance teams, etc., more and more is done digitally, and which means that there's more and more of a tendency for everything to leave a digital trail. So that's part of the transition, the fact that the data is kind of natively digital rather than sort of papers and forms and letters, etc. The second is that a lot of that digital data had fairly complex structures, or at least variable structures. Like you might be pulling some of that from particular documents that come from some supplier. There might be XML structures that you pull from APIs if you're interacting with computer systems. There's different formats for documents that have different levels of complexity and structure. And then finally, even though in principle, and I'll reiterate this point a few times, even though in principle you can often process all of this data into relational database structures for traditional analytics, it's time consuming and resource consuming to do that. You have to spend a lot of time thinking about how might we want to use this data, write the processes to do that transformation. And there's even then, there's still some risk that the transformations you do will not capture what is required for any kind of analytical use case. So it's in some senses, to get the most value out of this ever-expanding wealth of data, it's not really possible to in advance think of how you might structure it for those purposes. So those are kind of three driving trends towards having the development of both big data tools and the use of big data across many different industries. And there's an essential tension which you can see within all of these big data solutions. On the one hand, you want to be able, there's more and more data available to use, and you want to grab that and make some use of it. However, often doing efficient, cost-effective analytics on it requires imposing structure, which is sort of time and resource consuming. So there's a tension between those two things. And really you can think about almost any big data solution involves finding a trade-off between those two tensions and sort of and design decisions that find the sweet spot for the particular use case you're working on. So one of the things I thought it was worth doing is maybe quickly reviewing relational databases, because Bikesh was telling me that you've covered a lot of this in the course already, but it's worthwhile maybe just a quick review to put it in the perspective of how this relates to big data. I'm just going to move my camera icon so I can see my own slides. So the first thing is that, of course, the data structures have to be determined in advance of both storing and using data. So sometimes in the kind of analysis of these systems, they talk about this as schema on write, meaning you have to decide the schema of the data before you even write it to disk. And so that means that typically the data is stored as individual records, and they're often a discrete series of individual data points. So it could, for example, be numeric values representing the number of units sold, a date representing the date that they were sold, a category representing the type of product that was sold. You have this series of discrete data points stored in an individual record, but the entire schema of that has to be defined in advance. And then typically, if you have any kind of complexity to the structure, you need you need a primary key often to sort of look up the records in that data set, and it's the basis by which you form sort of join relationships. So in this really simple example here, you have the notion of a sale. There's an ID for a sale and an amount and a company ID and the date of the sale, but also the employee who made the sale is a foreign key in this table, looking up the employee ID in the employees table. So the structure is predefined, but also in a sense, the cardinality or the join possibilities are also predefined. And if you want to get sort of more complex relationships in these relational database systems, you need typically a join table. So a join table allows you to say, okay, I can't quite see. Let me move this thing again. In this example here, we have on the right, you have the membership of a department. You have two different tables, one for people, one for departments. And because it's a many-to-many relationship, you have this join table in the middle, which indicates all of the people who belong to each department. And multiple people could belong to multiple departments. Each department has multiple people, etc. So it gets complex. Cardinality gets more complicated to implement, but again, needs to be defined in advance. Now, there are the advantages of these relational database systems is that they're very efficient at querying data. You've got consistent and very, very well-established processes for creating and maintaining databases. So we've been doing this in industry for a long time, well-established sort of best practices. Also, there's a large workforce of people who have the skills to query data that is structured in this way. And there's a large ecosystem of tools that are already built for doing analytics and dashboarding and many other things. So you can integrate these relational database systems with many other types of tools. So massive advantages to using them, which kind of then begs the question, well, why can't our big data just go straight into a relational database system if there's so much advantage to it already? And in fact, if it was merely about the volume of data that gets collected, then perhaps cost would in fact be the only limiting factor. We could just throw more people and money at it and we could get all of that data in there. But there are a number of other complexities that I've kind of hinted at already, which means that it's not, even if you could afford to do it, it may not be the ideal approach. So there's let's talk about a few of those. The first is what you could call schema creep. So that typically big data, you're referring to data that you don't understand very well in advance of collecting and storing it. And the schema can vary dramatically depending on the source you're pulling the data from. So think about, for example, here's that trivial example I used before. With an employee, we know in advance that there's only these 4 pieces of data we want to collect about the employee. So the schema is kind of predefined and well understood. Now, if we flick to, say, a use case where we're working on collecting telemetry from machines in some kind of factory, we might find mind that there's several different machines, maybe they're made by the same manufacturer, but the content of the telemetry that gets sent back. So just for, I guess, in case people are not aware, the idea of telemetry is that machines can have internal diagnostic systems that might send packets of data back to some kind of collection service saying, this is what's happening inside me. And this can be used for many, many use cases in understanding what's happening across a suite of machines inside your factory. But the payload or the content of those packages might vary between machines. Like one might have a message talking about what's happening. One might have a sort of temperature measurement. Or in fact, as you get more and more different machines, potentially from different manufacturers, you might find the naming conventions of certain things change, or that the number of variables that are returned is highly variable. And in fact, if you're, as you cannot guarantee as time moves on that you won't be getting data points inside these packages when you onboard a new machine or upgrade a machine, etc., that doesn't clash with a pre-existing schema. So it's an ongoing, the more diversity in data sources you're ingesting into a system, the greater the battle you have with making sure that if you have to use an RDBMS, that you've got the schema defined and it covers all possible use cases. So schema creep is one of the problem, and a related one to that is sort of cardinality creep. So part of the unknown structure of files can be unknown structures of joins. Remember that the relational database system we spoke about before, you either have very simple joins between tables or using join tables for many-to-many or one-to-many relationships. But you do have to know what the complexity of the joins that are going to exist so that you can predefine that structure. We sort of showed that example before of the foreign key inside the sales table pointing to the employees table to identify the employee who made a sale. But continuing on with that telemetry example, you might find that perhaps some of the telemetry from the devices in your factory returns sort of more complex data types inside. So in this case, I've got this is what's called a JSON kind of representation of an array. The square brackets indicate that there's multiple components inside this thing here, and each component is what's in sort of JSON terminology is an object or a dictionary. So it's got a set of key value pairs inside it. So you've got sort of fairly complex, high cardinality data coming from this particular event. And there's no guarantee that, again, as we mentioned before, the more machines you get different kinds of cardinality that potentially indicates some kind of join relationship between other machines inside your network. So cardinality problems or simply not knowing the cardinality you're going to be collecting as you move forward is another impediment to imposing structure in advance. Temporal complexity is another one. So there's many facets to this. So time is often a really, really critical component of different kinds of analytics. So, sometimes you want to know the time that elapses between events and how that relates to something else you care about. You want to know which data points inside your database or your data structures are changing over time, and that typically, when there's data that changes over time, relational database management systems have either solutions that are proprietary. So there are sort of various database vendors that have very, very specific sort of change tracking solutions, or there are sort of general purpose, but probably slightly suboptimal solutions where you maybe have a separate table where you record the values, the time points at which the values in the main table changed, so that in principle you can sort of reconstruct the database at a particular point in history, but it's complex to query and so suboptimal in that sense. So often what happens is people come up with representations of time that they think are going to be useful for certain kind of analytical purposes. So for example, here we might have a field called days since maintenance that gets sort of updated on some regular basis, saying how long has it been since this particular device in our suite of devices was maintained. But in reality, if we're sort of storing things in a big data system, there might be a lot more complexity that we want to store just by dumping files. And it might be things like an ID for each maintenance event, as well as the date time that it occurred, the ID of the engineer who performed the maintenance, and maybe some logs about what was done, parts that were used, etc. And you can imagine these logs might have internal cardinality pointing to parts reference lists, that kind of stuff. So time-based data can have a lot of complexity that when we impose structures on it for specific analytical purposes, we're missing a lot of the details. So that is sort of another reason. And it's difficult. Often it's difficult to know all of the different ways you might query the way things have changed over time in advance. So in some sense, it's better to have the data available at its sort of at the crudest possible data collection point, and then deciding what to do later. And the final sort of topic here is textual complexity. So even though you can store sort of large text blobs inside a traditional database, these are still not particularly easy to query if you want to sort of know what's happening inside that text. And if there is potentially multiple sources of that original text, there is still, you have to sort of predefine specific processing and appending processes when you want to write that text into the database system. So often a lot of big data solutions typically involve just basically dumping files into folders and relying on that folder structure as your way of sort of determining what you want to query. And I'll talk a little bit about how that works as it relates to keys later on. So being able to just store arbitrary documents inside a folder structure and then sort of query it is a really, really useful aspect of many, many big data systems. So the summary here of sort of big data solutions in relation to relational database systems is that they allow you to store arbitrary files without knowing their cardinality or structure in advance. So these can be structured files like XML or JSON, or they can be just sort of raw text documents or other types of files. You can maintain this data as records about all the fine details of any event that's occurred inside the organization, whether that be kind of sales events or maintenance events or sort of machine generated telemetry data about what's happening inside across the organization, and that can be used for those future analytics use cases without having to sort of define how do we process that into sort of business intelligence data points in advance. And that you can keep collections of arbitrary documents that can actually be queried by other data sources. I mean, obviously there's usually some work involved in doing that, but being able to run queries across complex documents is one of the other big advantages of working with big data solutions. So how do these big data tools actually work and allow us to achieve these things? There's a couple of elements to this. The first is they typically use traditional and expressive programming languages. So one of the SQL, while it is a very, very purpose-built specific language for querying data that's structured inside relational databases. It's not a fully fledged and fully expressive programming language. So there's limitations on what you can do with it. And so that's one of the ways that the big data tools often achieve this extended functionality is by using more expressive programming languages. Secondly, one of the things they allow analysts to do is often specify just the parts of the data structure they want to use. So there is, and this is not true of all solutions, but there are some solutions where you can sort of ignore the full complexity of the data, that when it's not relevant to your specific project. And sometimes this is referred to as sort of schema on read. You can make use of parallel execution systems. So typically traditional relational database systems are built as monolithic structures. So typically designed, at least initially designed to run on single machines, and it's sort of centralized control. but big data tools are often designed to be parallel upfront. So they're one of the core elements of their design is that the way queries are constructed is that they can be broken up and run across many, many different machines. So you get computational efficiency through parallelism rather than sort of efficient monolithic structure. And they also work by breaking computation into multiple stages. So initially, and we'll talk about this in a little moment, is that this was done by writing intermediate results to disk. So a complex query is broken up into individual processing components, and the results of each component is written to disk, then read into the next one. So simplifying complex processes to individual processes with intermediate stages is one of the ways that big data tools have achieved this. So it's probably worthwhile talking about a few of the key technologies in this space. Now, it's worth mentioning as well that these are not the kind of probably the most used techniques today. Like the field has moved on a lot, and there are a lot of proprietary tools in this space. I think it's mentioning these three specifically because this was kind of the most heavily used initial big data tools, and all of the design decisions that went into building these tools have kind of influenced the field moving forward, and you can see echoes of them in almost everything you see in the big data world. So Hadoop is probably the tool that you've heard of most in this space, and it's basically an open source distributed file system that was built by the Apache Foundation or released by the Apache Foundation, but based on a paper that was originally released by Google. So Google had their own internal distributed file system. They didn't open source that, but they did release a paper describing how it worked, which led to the development of Hadoop. And one of the key technologies inside the Hadoop stack was something called MapReduce, which was essentially a programming framework for processing data inside these distributed file systems that worked by borrowing an idea from functional programming of the idea of a map and reduce. The basic idea was that you could read distributed files from this system and construct your queries as a sequence of map and reduce functions. So a map takes values and applies a function to transform it into something else. That's the mapping part. And then the reduce is a kind of aggregation. You say after the mapping is done, you'll have a key value pair. You aggregate everything with the same key together and apply some other function to it again. So it's quite remarkable actually how many complex processes could be reduced to a series of MapReduce functions. And that was really the success of MapReduce as a programming framework for distributed computation is really one of the key things that led to the boom in big data tools. Now, Hive was another open source technology through the Apache Foundation, which allowed you to do SQL-like querying over data stored in Hadoop. So basically it allowed you to sort of specify a schema on read that you then applied to a directory structure where it could find CSV or JSON or XML files, etc. And then it gave you an SQL query language that you could then query that. So this was kind of one of the first ways that people who had been sort of SQL analysts could start querying data on these distributed big data systems using tools they were already familiar with without having to sort of go to the trouble of designing and specifying database systems over the top of them. And then Apache Spark was a secondary wave of data processing on distributed systems that used an entirely different model. The idea was that they wanted to be able to do slightly more complex transformations than had been done with MapReduce, and they also wanted to do it in a way that didn't require you to continuously write intermediate results to disk. So Apache Spark was built on the top of an initial paper that talked about the development of something called a distributed data frame. So the idea that you could have a an in-memory data structure that was distributed across many machines, and then a computational framework that allowed you to process that in-memory data structure. And Apache Spark led to sort of the development of the sort of multiple proprietary systems that have been built on top of it, and sort of formed. There's many sort of data processing startups that expanded from that space. And all of these tools, as I mentioned before, have been a big influence on the big data world moving forward. So use cases for big data. So there's a couple, I mean, there's many different things you can do with it. Here's some of the most common ones you see it across industry. So any kind of organization that does fairly extensive document processing often has a use for some kind of big data analytics. So particularly if there's like, you're processing documents of different forms that aren't particularly well structured. Say, even if it's things like where you're sort of scanning paper documents, storing them somewhere, even if you've got human teams looking at them, you will typically have a large archive of these historical documents that could be quite useful for sort of analytics projects to understand what's happened in the past. The topic I spoke about before, where you've got sort of maintenance or machine logs. So machine telemetry is a massive potential for big data analytics, because you've got enormous amounts of what you might call semi-structured data that can vary considerably between different machines and even over time. Web application logs. So this can be for things for like the company website or the intranet site, or sort of back-end systems if you've got mobile phone apps, that kind of thing. Those logs can be absolutely massive, and again vary between different applications, but can be really useful for different kinds of customer analytics. So you might want to understand the journey a customer goes through, like how they sort of come to the website, the process of signing up and becoming a customer, how they move, how their kind of product holding changes over time. Another really common one is understanding how the path of the customer through your various software applications leads to churn, potentially, just understanding what's the behavioral patterns leading up to a churn event. So churn meaning here when the customer chooses not to be a customer, either say canceling account or ceasing to purchase goods from you. And then it can also be used, it's a rich data set for potential customer segmentation, just understanding what are the different classes of behavioral patterns in the way that customers interact with you. And then the final use case is around kind of security or internet security analysis. So again, any company intranet consists of many different servers interacting with each other. So there's constant web traffic, and often analyzing this to try and understand when there's malware on the system, or sort of people actively trying to penetrate the system. There's these big data tools are very useful for analyzing the massive amounts of network data. But the key, as you might imagine, for a lot of this is really understanding how you can bring the worlds of big data analysis together with traditional data analysis. And as you might imagine, a lot of that comes down to the keys. So how do you join data from one set to another set so that you can complete the analysis? Because often the things you care about, like say the cost of a product, the revenue, the value of a customer or a loan, etc. These things often reside in traditional database systems. So the things that are probably most important to the business reside there. And often big data is only being used as a supplementary data source to try and understand additional complexity inside the business and how it relates to those key business metrics. So there's a couple of things that you probably need to keep in mind. Often, if you're using some kind of semi-structured or structured data in things like XML or JSON, there's potential for there to be IDs inside this, but you need to make sure, does it use the same identifiers as your traditional database systems, or do you need to develop sort of mapping tables or sort of import mapping tables from external vendors? And then the second thing is that often this can be achieved through directory structures. So it's very, very common in big data systems to structure data through a hierarchical directory structure, and often using date as the main, like, so this kind of structure here where it's like, it's sort of year and then quarter and then week, or often it might be sort of year, then month, then day. There can be, typically time is often used as a way to structure the collection of data. And then you need sort of methods for then joining that time structured data against the entities that you care about in your analysis. So that's a couple of the ways that you typically bring the data together. But in both instances, it does require a little bit of forethought, although the sort of the time-based structuring is something of an industry standard. So pitfalls. As you might imagine, there are quite a few pitfalls that can occur when engaging in big data projects. Typically, it requires a stronger programming skill set than you might have amongst your sort of business analysts team. So as I mentioned before, these big data systems often rely on fully expressive programming languages more so than SQL. So and it's certainly not true of all use cases, but in some use cases, you're going to need people who have more extensive programming experience. Typically, it requires very focused sort of hypothesis-driven work. So one of the disadvantages of having enormous amounts of detailed data is that it can lead to a process of constantly just mining for interesting patterns. And that can become fairly unfocused fairly quickly. So you do want to make sure that each analytic, you know exactly why you're going to the big data solution, and you know what you expect to get from it. And so that's what I mean by hypothesis-driven work. And then finally, there really is an investment in the infrastructure and ingestion process to build up all of the assets you're going to need to deliver results. It's not something that you're going to be able to sort of turn on overnight. You do have to have, your big data solutions require their own infrastructure, and they require the development of new processes for sort of ingesting that data. So pipelines, as well as things like that kind of directory structure that I spoke about before, for making sure that the way the data sits on disk is something that you can query and join in a sensible fashion to join and get value from in relation to what you have in your traditional data warehouse. So the overall summary we have here so far is that big data generally refers to unstructured data that's now routinely collected by organizations of all different sizes, where everything the organization is doing tends to leave some kind of digital trail. So it's not, you've got less and less elements of the business process being done using, say, paper documents or manual deals. It's greater and greater trend for everything to leave some kind of digital indication of what that particular business transaction involved. Now, in principle, and we talked about this idea a few times, much of this data could be stored in a relational database system. However, the costs and time for doing this are prohibitive. Like, it takes a lot of time to both think about how to structure that data, design those schemas, and implement them. And then there's no guarantee that it's going to satisfy all the potential use cases you might want to focus on. So it's really about the trade-off there is you don't want to prevent yourself from being able to do explorations and experiments that are the sole reason for collecting this data is so that you've got open-ended exploration to understand processes in the business, and that is one of the reasons not to decide in advance what the structure should be. The general big data philosophy is grab whatever's available, store it in a kind of semi-organized fashion, and then apply just as much structure as you need when the analytics needs to be done. So that the data is available and you don't need to sort of waste resources on imposing structure before it's actually needed. But as we sort of mentioned before, you do need to think through the process of what kind of keys are going to be available to sort of join the data, so that because the big data is typically not, it's often supplementary to the things the business really cares about. So you need to be able to make sure you can join it back to those key data points to complete the analysis using your standard analytics tools. So I hope that was useful for everyone. Thank you for your time. And please reach out to me if anyone has any questions. I think that went a bit quicker than I expected it to be, Bikesh. Apologies.
And no worries. I think that was really nice. It's like 2:38. So what we will do is we'll take a pause and take about a 5 minutes break. And then after that, we'll have a question and answer session or some interaction session.
Yep.
So we together with our student will have some interaction, and then I will summarize, after which we'll wrap up.
Great.
Perfect. So 5 minutes break. And let me stop the recording for the break. It's 12:38, lesson 39. We'll get back at 12:44.
Wonderful.
Let's get some water, coffee, or recording. Yes, welcome back after the short break. And I hope you had a chance to grab a coffee or water or refresh yourself for the second stretch of the lecture. So we have a couple of students in the lecture. Do you have any questions to our guest speaker, like regarding the topic of big data? So if you have any questions, just type in. And meanwhile, so let me ask something, John, so something that students might be interested. In data analytics, what happens is we start with the relational data model, right? So we talk about relational database system, we learn SQL, and all of a sudden when you start to hear about big data is everywhere. Big data is the data is the next big thing. It's the oil of the modern economy and everything, and the big data is going to overwhelm, right? So in this context, so what's your opinion? Is it still important to know the relational database, or what is the role of the relational database for the businesses?
Yeah, so I think it's like, I think the first thing it's worth, I've never met a data scientist that wasn't still using SQL somewhere in their job. The reality is that not only with, like, there's lots of important information that resides inside relational database systems. There's lots of SQL-like querying languages that work over the top of big data systems. Even many of the proprietary systems have their own flavor of SQL. It may not be able to achieve everything that you want to achieve, but you can certainly achieve a lot with it. So SQL doesn't appear to be going away anytime soon, even in the big data world. It's just that it's worthwhile being aware that like anyone, as the more time you spend with SQL, the more you become aware of just the more complex the thing you want to do, how cumbersome it becomes. So I think if you get to the point, often what you'll find is, if you're familiar with a language like Python, for example, as well as SQL, you'll find that there are certain things you want to do in SQL that just take lots and lots and lots of lines that are very, very simple to do in Python. So there is a trade-off. It is definitely worth learning a more general purpose language, and Python is an excellent candidate if you want to be able to do sort of more advanced things.
And this is an excellent point that you mentioned, John. I started learning Python. I use R and Python or Java. I started from like hardcore programming, and I learned SQL quite a bit late. And when I learned SQL, I could see the programming logic or the logical thinking. It's not so different from how you use it in Panda, let's say for data extraction and data manipulation. It's not massively different, right? The logic is almost similar. There's only little bit difference in syntax. And this is excellent point you made, is like, if you want to have a good career in business analytics, knowing SQL is still handy and quite valuable, because you can always take that thinking or that logic to other programming languages, and you'll encounter something similar. In this course, most of the time what we say is that if you have a relational database model, if you know how to get the relational data from relational model or get the data from data warehouse, you could still solve 80% of, let's say, trivial regular business analytics need. And then there are 20% of like a analytical need or problem that you can solve with the big data, which are more of high risk, high reward. Do you agree with this statement?
Yeah, I think that's, I don't know what the exact percentages would be, but I think that seems fairly reasonable to me.
Yeah, I think so. Basically, based on your experience, the project you have worked. So, what are the challenges that companies find when working with big data? Like,
Yeah, there's many different challenges. I mean, one is the like one of the challenges has been that many of these things have just diminished over time, in part with the transition to cloud. So if you talk about, like, if you go back 10 years ago when companies were cloud didn't really exist, like except in like a very, very limited form. And companies were experimenting with Hadoop, but they weren't super familiar with the idea. So one of the ideas of Hadoop is that you get cheap commodity hardware, but large amounts of it to build a cluster, and then you use that to ingest data. But a lot of large enterprises are much, and they're more used to having sort of contracts with external vendors who provide hardware, and they sort of guarantee some of its success. So the problem that, sorry, they guarantee they have maintenance contracts for it. So what happened is large enterprises were building Hadoop clusters that cost them way more than they should, because they were using high-end machines with these high-end maintenance contracts, rather than fully adopting the Hadoop mindset, which is lots and lots of cheap machines, redundancies already built into the things. So you don't need those maintenance contracts. So there was like cultural aspects of the way IT had been done in enterprise organizations, which it like prevented them from really embracing it. And the second thing there was that meant that you needed to then, there's a lot of, so even with, like, initially at that point in time, even though there were SQL like tools for querying that data, the problem was often you still needed to have some familiarity with, say, SSH and the Unix shell in order to get into those systems and run those queries. So there was still an impediment for traditional business analysts who weren't super comfortable with the ideas of working with Unix. So there is kind of there's a training barrier, I would say. And then the final one would be things around the kind of security elements. So I guess organizations have really, really well-developed policies for how you identify which data is secure and who has access to what. And a lot of those kind of restricted data policies were and probably still are somewhat undeveloped on open source big data systems, and you only probably really get something like that if you basically go to a cloud proprietary vendor, if that makes sense.
Yeah, definitely. And then, at least from my experience, listen, when everything started at the beginning, the companies started to collect the data without thinking about that. You really mentioned it nicely in the presentation about the hypothesis. It was like almost like a gold rush. Let's get whatever is available and let's store it. And then all of a sudden, you could see the data scientist or the analyst being overwhelmed with the data. So here's the data. Now, storing data and getting data costs you something. Let's get value out of the data. Right? It was almost like value driven rather than the problem driven. And then all of a sudden, you have a data scientist who is sitting at the data dump that is terabyte, and then they are being pressured. There's an immense pressure to generate value out of that, and without proper problem formulation or framing. And I think we have pushed that stage now, because now companies are receive more support in terms of like how they can reprocess the data, get the analytics out of that, so they don't need to just sit on the raw data. And also there has been better education around the data, right? Like how companies should handle data, and then start from planning what data you want to collect and so on.
Yeah, 100%. Like, I think you're right that we've somewhat moved beyond that stage, but it's worthwhile sort of keeping what you say in mind, because it's an allegory of things that always happen in business, which is that new techniques and approaches become trendy. Companies throw lots of money at sort of wanting to incorporate those systems into their stack. and then they put pressure on people to use those systems in order to get value to justify the original expense. So this is like this sort of cycle of hype is something you will encounter over and over and over again in your career. And I kind of think it's like, it's just one, I think it's like the way we develop a culture of responsible analytics people is to always push back on this and say, no, like, because they executives will, there will always be executives who will respond well when they realize, oh no, yes, actually we do have to focus on real business value and on the customer and on the product, etc. And that's, it always puts you in good stead in your career.
Yeah, definitely. Yeah. And then I can share you another instance of like how people have a misleading concept of big data, right? Big data is not always big. That's one of the experience. Let's say I had a company that came up with the browsing data of like 170 million customers. The data file was terribly big, so almost hitting close to terabyte. And when we started to scope the problem, when you start to scope the problem, start to like trickle down the relevant piece of data, and all of a sudden we are looking at 100,000 of record, right? Or from 200 million, right? So sometimes we have that the false sense of like we have enough data, right? I see this as a red flag in most of the cases when companies say that we have a big data. Definitely, there is a big data. The question is, what percentage of that data is relevant to the problem that we are looking at? Because most of the time, that's pretty small, and sometimes not sufficient to build a good analysis out of that.
Yeah, 100% true.
Yeah. So so do you have any suggestions for our students, like how to prepare for an analytics job, what they need to focus on that, on like what kind of tools they have to learn or how they can prepare?
So yeah, I would say, like, I mean, one thing we've already mentioned, SQL remains important. You use it all over the place. I've used it. I've used many different varies of SQL in almost all jobs that I've had. You know, I've used sort of Teradata flavors. I've used MySQL flavors. I've used the Hive flavor. There's a BigQuery flavor that gets used. You know, it's on the Google sort of proprietary system. There's many other flavors in different systems. So it's always good to sort of have that in your bag of tricks. The second one would be learn a Python or R, some kind of general purpose language, super useful. Not at the least of which is because it'll help you get that kind of algorithmic thinking process, which is sort of critical to this, thinking about the sequence of transformations you need to make to the data. The final one is two final pieces of analysis, things that I would say that are just general skills and approaches that are useful on almost any problem you look at. The first is that it's really important to think critically about how you're going to measure the success of what you're doing in advance. So like, almost like in the way that sort of software engineers do sort of test-driven development, where you define how you're going to test something before you even build it, and then maybe build the tests first, so that you know what you're aiming at before you start aiming. And then so you can, it doesn't matter if you refine those as you go along, but having that notion of what you're aiming at to begin with is really useful, and as much as possible, try and align that directly with business outcomes. So I see far too many people but this is more of a kind of data science, machine learning engineer kind of problem, where they'll report on standard metrics like root mean squared error and report that to business executives as if that's somehow meaningful for the business process. That those standard metrics we use are a combination of things that are convenient for us to compute, or things that we can create gradients on so that we can optimize processes for them. They don't relate directly to business outcomes. So it's always better to have systems for generating, even if they're estimates of business impact. It's really useful for your stakeholders to have that. And the final one is, it's really good, and I would say it's embarrassing how late in my career I learned this, actually, is that it's worthwhile having a suite just good baseline models that are sometimes they're like what's like, think to yourself, what's the most simple, naive thing I could possibly do that doesn't use any statistics or machine learning? And let's evaluate that, see how close that is to getting us the value we want. And then let's talk to a couple of people and come up with a simple formula or a simple kind of representation of the status quo of the way that people understand the business, represent that as like a formula, and then evaluate that as a solution. Because those baselines can often tell you, I mean, sometimes it'll turn out that it's really hard to outdo them. Sometimes they just give you a sense of, if we're going to spend all this money building and deploying a fancy machine learning model, what's the kind of lift we're going to get over these simple baselines, so that the business decision of the costs of implementing that versus the expected reward is really, it's a really easy equation for executives to analyze.
And I think you made an excellent couple of points here. One was like how to relate what you do to the business measure so that you make people understand. For instance, you might have a performance in terms of accuracy, how accurate your model is, but then you can give a rough estimate of business value loss that can cause by like 1% accuracy. So how much, and then that will also help you to think in terms of like what model to use. And yesterday I had an interesting discussion with one of the students on like how to finalize our assessment and like how to attend the final assignment. And I was exactly giving you the same suggestion. And this is what we try to teach our students through our assignment, because you cannot teach this during the lecture, you cannot teach during the tutorial. So what we say in assignment solution is that it's really important to have a planning, think about what you want to do, what's needed, right? Just what you have and what you need. Sometimes what you need is different from what you want, right? You almost always don't get what you want. So most of the time you need to work with what you need to do, and then start working with simple model, try to get some basic solution, right? You have some basic model. Let's say if you get model with 70% solution, doesn't matter, it doesn't have to be perfect. Start writing report, building something one at a time, so that by the time deadline comes, you have something to show. And that's exactly what baseline is, right? What you meant. Try with something simple that you can do dirty and fast, quick, to see if it makes sense. Then you start to see how much effort you need to improve that. What are the costs? Listen, most of the time, I talk with some of my friends who are data scientists in the industry, and they say that like 80 to 90% of business problems, they are solved by using tabular data. And like, let's say, simple model like a random forest or XGBoost, or logistic regression, those are sufficient, right? So you don't even need a deep learning model, because they have associated cost with implementation and deployment, and the marginal gain that you get, they almost always don't justify.
100%.
Complexity.
I see that over and over and over
Over
again.
every year. And this is very important point you mentioned, that don't buy the hype. Right, that's a really important. See what's needed first, like get the baseline model, see the improvement, see the trade-off. The key word here is a trade-off, right? Trade-off between the simple model and the trade-off like of a highly sophisticated algorithm. And then one needs to evaluate that before making a choice. And this was an excellent point that you raised. And I hope this is really helpful for our students. So let's talk a little bit about something on different topics. So what I mentioned to my student about like a data visualization seems pretty straightforward, because dashboards are on rise. We know that a lot of companies use Power BI and everything. So however, I am of the opinion is the data visualization is one of the most difficult skill, or something more challenging. Especially if you're working with big data. Right, visualizing with big data is not always straightforward. So, what's your opinion about this statement, or like your experience with visualizing big data, generating visuals from big data?
So it's certainly true that data visualization is like a field in and of itself. Like it's certainly. I mean, so it depends in some sense on who the target audience for the visualization is. So most data scientists are capable of constructing a visualization on an ad hoc basis that answers the kinds of things that they want to understand as they're going through a sort of development and analytics process. So visualization for the sake of as a kind of like as part of that investigation is, you know, can be challenging on big data, but typically they'll take samples and they'll be able to work with it. I think the topic of visualization for end users, whether it's sort of business stakeholders or clients of the company, that's a kind of a very, very different thing, because then often you're dealing with people who have varying degrees of statistical knowledge and sophistication. So you're dealing with people who will have different expectations of what even a mean. What does the mean mean? Like people have different expectations of that. So you know, catering the visualization to the fact that you don't even know that they'll have the same shared background knowledge, super hard. And there's all kinds of biases that go on in human brains you have to deal with. So I think it's definitely, you know, if this is kind of a mission critical thing, particularly if it's going to be seen by customers, you should have someone who's an expert in data visualization on that, and probably a few people to act as kind of like naysayers to sort of challenge things that are being said. But I would also say that internal dashboards, I'm one of the things that like, so there is a tendency in business to fetishize dashboards and just build dashboard after dashboard after dashboard, because it's kind of like part of the pathway to busy work. I mean, people feel if they're building things, it feels like they're being productive, and the manager of that team feels like the team's being productive because there's more widgets being added to the dashboard and they can see more of what's going on. So everyone feels like they're being busy. But I think I've got it. Here's an anecdote from, I won't say which company this was in Australia, but I know someone who sort of took over an analytics team there and found that there were just dashboards galore and reports being created all over the place, but there was no documentation of who used those dashboards or reports whatsoever. So he basically went through this empirical process one by one. He just turned off the reporting for those dashboards, and then he waited to see if anyone complained. And then, like, if no one complained within 3 months, he just deleted it and it was gone. And he reduced the kind of the number of dashboards by well over 50%, because large amounts of this stuff just wasn't being used by anyone. So I think one of the things that I advise people to do is everything that's shown on a dashboard should be connected. So the primary dashboard should be connected to decisions. If you can't look at a plot or a statistic or something and say, what decision would I make when I see this, or when I see it goes over a certain value, it's probably not adding any value to anyone else. It's just part of a dashboard fetish. The only exception to that would be like maybe if there's like on secondary dashboards where you may be trying to drill in and do diagnostics, there might be plots that the most of the time when you look at it, it's not informative, and you've only gone there because you've seen something in the primary dashboard that says, okay, I need to do further diagnostics. But by and large, I would recommend always like just pushing stakeholders and executives, regardless of what they're pushing you to put in a dashboard, try and get concrete indication of the specific decision they'll make on the basis of every single widget in that dashboard. And if they can't name those decisions, there's a good chance that widget is not adding value.
Perfect. I'm really glad that I asked you this question, because this was really nice insights, right? Because we often get a question from students like, what should I keep in the dashboard when they solve this assignment? And this is the exact kind of suggestion they need, right? Think about what kind of decision-making decision you're going to make. And this is exactly what is different from workplace to the university lecture. In university lecture, a lecturer tells you, give me this visual. And in workplace, nobody tells you what visual you need to get. You need to find it yourself. Talk with people and see what makes sense, what is useful, and so on. Else you will end up in the situation that you mentioned, where you have inlays of like those kind of widgets and dashboards that people actually don't use at all. And maybe that has something to do with incentive or performance evaluation, because I mean, we know that data science and IT is a lot more than technical. There are managerial, human, and social element intertwined, and that makes it more complex. And this is a really excellent insight.
Thank you, Vikesh. Yeah.
Thank you, John. So a quick, before we can continue, look, so I enjoy so much chatting with you. Before we continue, keep on like chatting, a quick check with our students. Does anybody have any specific question or anything that you would like to ask John? please feel free to unmute yourself. And also we can see thumbs up from Chunking Doos. I think the student is enjoying and learning something valuable. Benjamin, if you have any question, but please feel free. And same applies for Hui. So you can definitely join the conversation. Perfect. In this course, we also discuss, in addition to like this data analytics, so we also talk about the organizational and societal and ethical issues of data analytics. Now, how do Australian company view the ethical issues, or let's say the societal impact of data analytics in your experience? So what are the major concerns for this for the data analyst, let's say, in terms of ethical concerns?
Yeah. So, I mean, a lot of people are certainly talking about it in Australia. It's probably not as hot an issue here as it has been in the US, for example. Part of that is because I think, it depends on what industry you work in. So, for example, if you're working in finance, for example, there's already really, really strong regulatory guidelines about the kinds of data that can be used for specific kinds of purposes for particularly ethical reasons. So, for example, there's guidelines around not using race, ethnicity, gender in credit decisioning, for example. And in fact, often that extends to sort of analysis done by auditing firms as to whether you've even got proxy variables in there for those things. It's obviously not, it's hard to sort of perfectly eradicate all of that stuff, but these are things that people are aware of and consider in their modeling solutions as you move forward. And similar things are kind of emerging in other industries. I would say that there's a couple of key things that that people are aware of, at least I've heard talked about in Australia. The first is that it's not emphasized enough, the fact that it's not like analytics solutions create the kind of the ethical dilemmas. These ethical dilemmas pre-exist, and they exist inside the data sets in and of themselves. So the primary concern is not that we create the ethical problem, more so that we harden it, like we make it becomes harder to eradicate because systems are built in which it's kind of hard coded into the solution. So that's kind of the first main point. The second main point, and this is probably less openly discussed, and that is that one of the problems is that you have to sort of decide what your kind of ethical principles are. And in some sense, I would say a lot of organizations have been quite happy to sort of play in this gray area, like because everyone is kind of aware that people have different opinions about many of these topics, and in some sense, once you take a firm stand on them, you're now signaling to the customer base where you stand, and it's a possible sort of point for differentiation. So I think a lot of companies, there's a fine that they have to decide what are the things that we definitely stand for, and what are the things that we're happy to leave in the gray area, so that we can have sort of customers who potentially disagree with each other on these topics. Does that make sense, Bikesh?
Perfect. Excellent. Because in recent years, I had seen a rise in people like biased AI, biased algorithm, or like ethical AI and so on, unethical AI and so on. And then that has always been my stand, right? Algorithm is an object, is an artifact. It doesn't do anything at all. What it can do is it can either suppress or amplify any existing biases in data, right? In that sense, it's a non-factor, right? The factor, what you already mentioned, is that the biases lies in the data. It's encoded, hard-coded in data. And sometimes they are pretty observable. Let's say ethnicity and race, you can directly see that sometimes it's hidden deep down. Like there could be a proxy variable. For instance, you can have a postcode, and certain kind of postcode can lead you to infer about the races of people, like particular races or group of the people. If you could cluster, you could perfectly cluster them. And there could be some subtle variable in the data that is not obvious or visible in the first instance. You might be aware of Amazon hiring assistant, AI hiring assistant. that
Yeah.
used LinkedIn data. And after 3 years, it was found out that it was recommending female candidates because it could infer gender based on the hobby description.
Yeah.
And that was one issue. Second issue in the data was that historically, Amazon had a higher probability, like Amazon mostly they hired a male candidate over female candidate. So basically the probability was already biased toward male candidate. So basically what the model would do is infer the gender and then only make a decision. Now I think the ethical issue becomes really critically challenged, especially even when the students are submitting assessment, right? They might develop, they have all the variable, they might develop a perfectly fine model that is 90% accurate, and then they remove all these variables that can lead to ethical conscience, and all of a sudden they drop, the performance drops to 60%. Now,
Yeah.
I think the similar scenario might also be quite like common in industry. And then it's all about, like you mentioned, about company philosophy and what they believe, where they stand, what they prioritize, and how they work. So I think this can be a really interesting issues moving forward. And there's a separate field called data debiasing, right? Where there are algorithm methods that are advised on like how to debias this data. So if some students are interested, you can look for those, right? For instance, one of the method would be use all the variable and predict the gender. And if the prediction accuracy is pretty high, you cannot use that data. So basically, it's a reverse engineering, right? You make the prediction performance on gender poor, right? And then select the variable, and then once the prediction performance is poor, then you use that for actual prediction. So there are different ways of learning or using, being creative, but then John excellently mentioned that it's all about what you believe and what you want to do, and sometimes it's also about the regulatory framework and so on. So that was an excellent point. So it's almost 15 past 1, and then we can take a break. But before break, we can check with our students if anybody has any question. Like, do you have any question, Benjamin, Chong, and you? So we can just please feel free to ask question. This is your opportunity to learn from the industry expert. We often don't get, that's only like a couple of times we get throughout the course. And this is also an excellent opportunity to build your network, because I know some of you will be in job market, right? Any question, guys? If not, let's take a break. And thank you, John. Thank you for your presentation. I will continue from here for our regular lecture, and I'll see you tomorrow.
No problem. Thank you, Bikesh. Thanks, everyone. I hope it was informative. Please just reach out.
And let's give a round of applause for John for his time. Please. Yeah, definitely. This is really much appreciated. Yes, I can see. Perfect. Thumbs up. Give me a thumbs up or give me a round of applause if you're still there. You enjoyed the lecture. Yes, perfect. Let's go for a 5-minute break. And thank you very much, John.
Cheers. Thanks, mate.
Have a wonderful day, and we'll see you later.
Likewise. Perfect. Cheers.
Cheers. Bye.